Welcome to the video tutorial on model validation. So what we're interested in here is what if we have a bunch of models that we need to predict or choose between, and one of the things that we might need to know is how to choose it and what are the criteria on which we should choose it. So the first thing we need to know is, what are we going to use the model for? If we're using it for prediction, then we're probably going to want one set of criteria. If we're using it just to understand relationships, then we're probably interested in using a different type of criteria. Now, prediction of future values is going to require us to use predictive performance. And predictive performance is usually involved with a lot of data splitting, so we'll be talking about that. One of the things you're also going to need to know is the structure of the data, because if you have really structured data, it might be very, very difficult to do predictive performance in certain manners. So just keep that in mind. Also, you also need to keep in mind of the complexity of the prediction procedure. So, for example, if it takes, let's say, 10 hours to fit your model, and you need to do something like 10-fold cross-validation, that means you're going to have to fit your model 10 times at 10 hours each. So that's also going to cause some issues with the complexity. So just keep that in mind, that when we're doing these model validations, we need to think about all of these instead of just trying to think that there's one hammer that works for everything. All right, so if we're just interested in understanding relationships, what we can use are just fit statistics. The things that you've seen, regular regression, you've seen things like R squared, adjusted R squared, mean squared error, mean average percent error, things like that, or mean absolute percent error. People are used to these things, and they've gone a long way. And if you're just interested in how well your model fits so you can understand the relationship, these are all fine. Other criteria that people can use are AIC, BIC, lasso. Those are penalized likelihood methods. They all work reasonably well in order to determine whether or not you have the best model across some models. And most people are quite happy with these. Now, if we're interested in prediction, we really need to change our thinking. Okay, we want to see how well we can predict data that the model has never seen. So this is where we're going to have to split the data and hold out some. Now, predictive sums of squares is usually the first one that most people see. This is called press, and it's used in regression, where you hold one out and then you fit with the remaining data. Then you repeat this until each observation has been held out exactly once, which means if you have a data set of size 1,000, you're going to do this 1,000 times, because each observation gets pulled out, the model gets fit, we predict that model or that value back, and then we calculate this sums of squares. Now, it's really popular in regression, but is computationally expensive. All right, so there's also data splitting, which is what we're mainly going to be focusing on, which is a single split. We've did these in a few other videos where you'll split the data and you'll say, this is my training set and this is my validation set. Sometimes you might want to do multiple random splits. So do this across many different training and validation data sets, especially if your data has some weird structure to it. This may be as best you can get as this multiple random splits, because you need to keep certain structure inside of your data, especially if you're doing things that require you to predict at a patient level, and you have patient level data, but you have a model that sits above that. If you know what that means, then it'll make sense to you, because each patient still has to remain in every single model in order for it to work. All right, so K-fold cross-validation. Now, this is considered the gold standard of data splitting techniques, but sometimes you can't do it. But if you can, nobody will question how you did it, because basically you're going to partition the data into K parts, which are formed into training and validation sets. Each observation is only one of the one validation set. But it's in every observation is in a validation set as well. It's quite useful. Most people like it, and if you can pull it off, then most people consider that the gold standard, often with K equal to 10. All right, so how to partition. So the question is do we want 2 or 3 sets? If you talk to computer scientists, they're adamant that there must be 3 sets, always 3 sets. If you talk to other people, they're like, well, it kind of depends. Okay, we definitely need a training set. We need some data to train the model on. That's not an issue. Then there's what's called a tuning set. So suppose we have other parameters that are not in the model, then one would use tuning parameters to set this. So for example, if we're obtaining out of our model probabilities and then we wish to use that to classify, we may want to adjust the cut value for the probability, and that is an adjustment we would make, and we would use a tuning set to do this. Now the validation set, this is used completely to see how the full model with all the extra parameters and everything can predict things it hasn't ever seen. Okay, and then here the thing is if there's no extra parameters, then we don't need a tuning set. And I would say statisticians prefer not to have extra parameters that we actually have to pick. We like the model to be estimated completely from the data, but sometimes you're forced into a situation where you do need to choose some values. All right, so how to use this for model selection? Okay, so the first thing we need to do is develop a model space. It might be just two models. I'm going to use this model and that model. Or I might have a total of M models, okay, of which I'm going to get a training, tuning, and validation set. And they need to be the same across all the models. So we're checking exactly the same across every single model. That way we're comparing apple to apples. Also, you must use the same metric on all of them. I know a lot of people will start mixing things up. And these are simple mistakes that people make just because they haven't thought through it. The training, tuning, and validation data sets, remember, we're splitting these things randomly. So if I run it again, things are going to get split again. So my training set and my validation sets are not the same, so that could be a problem. All right, we need to use the same metric. And what are some common metrics? The mean square predictive error is really common. It's just the mean MSE, and this really should be divided by n. I just didn't do that at the moment. I'm not going to do n minus p because if you have a neural net that has 17,000 parameters in it, that might be a little bit crazy to have to divide by that. But what we can do is just look at the MSE, this would be the sums of square predicted error, and that'll work fine. It works fine between different models. And this is if you have a continuous outcome or a numeric outcome that it's easy to see, okay, we predicted 5 and the real answer was 6. We can get a difference. Subtraction makes sense. Here, the correct classification, well, if we're trying to classify things, we want to know, did we get it right? So this is the correct classification rate for model MJ. You just take the trace of what's called the confusion matrix associated with the model and then divide it by the total number of entries that you have, or the total number of observations. And this gives you the correct classification. Now, there are other metrics that could be used, but these are the most common. All right, so the next few videos, we're going to be using these in practice. So I'll refer back to them, and you'll see how they get deployed in various areas, and we'll see how well they work or don't work, and see what kind of sort of inferences or model selections or evaluations we can make from these. All right, see you there.